So exercise 11 says determine the true value for each conditional statement. So we have if 2 plus 2 equals 5, then pigs can fly. Now notice this is a P then Q kind of statement. And we have certain truths values for each of them. This is true, and this is false. 2 plus 2 equals false. Equals 5 is false. And then we can also have pigs can fly, which is false. So this is a false implies false situation, which is true. Remember, this in the implication, this is a true statement. Now, if 2 plus 2 equals 4, this is true, implies something false. Pigs can fly is false. So this overall is going to be a false, since in the implication, the only one that is false is true implies false. Now, 2 plus 2 equals 5, then two plus 2 equals 5 is false. This will be a false implies true, which is true. 2 plus 2 equals 4, which is true, implies 3 plus 3 equals 6, which is true. Then true implies true is also true. Now construct the true table for P implies Q and Q implies P. All we can do P, true, true, false, false. Then we're doing Q, true, false, true, false. We're doing then P implies Q, which we know is true, false, true, true. And now Q implies P will be backwards. So true implies true is true. False implies true is true. True implies false is false. False implies false is true. So we have these values. And now if we do the last one, which is P implies Q and Q implies P, then we have true and true. This is true. False and true. This is going to be false. True and false is going to be false according to the end rule. And true is going to be true. Remember, we're using the values in these two with the connector and. So the connector and is true only with both of them are true. So true and true gives me true. And anything else with a false is going to give me a false. Okay. All right, question 13. So we want to rewrite each statement here and in the if-then form. So this says studying regularly is sufficient for passing the course. So because this is sufficient, this means that this is a P implies Q situation. And so if I study regularly, then I will pass the course. Now, having a valid ticket is a necessary condition for boarding the plane. So notice that having a valid ticket, this will be a Q implies P situation, right? So if I'm saying having a valid ticket is necessary for boarding the plane, this will translate to if I board the plane, then I have a valid ticket. Remember, this is what it means to be a necessary condition. Now, being a U.S. citizen is necessary and sufficient for voting in the U.S. federal elections. So we can just rewrite this as a person can vote on U.S. federal elections if and only if is a U.S. citizen. Okay. Now, question 14 gives me a couple of statements. So we have P equals N is even and Q N squared is even. So it says, which of the following correctly express the statement N is even only if N squared is even? Now, if you think about it, this is pretty much N is even is the P. And then this is a Q situation, right? So the phrase P only if Q means whenever P is true, then Q must be true. So Q is a necessary condition for P, which is exactly P implies Q. Okay? All right, moving on. Question 15. We're going to use a truth table to determine if these are logically equivalent statements. And so, of course, we're going to build our truth table. We need to do P, true, true, false, false. We need to do this every time that we need to do a truth table. Now I want to do P implies Q, which is true, false, true, true. And then the negation, of course, negation of P implies Q is just going to be the opposite, false, true, false, false. Now P and not Q, well, first I'll go with not Q. So I'll have false, true, false, true. And we're going to have P and not Q. And so P and not Q. Then we're going to check column P and column not Q. True and false is going to be false according to the AND rules. True and true is going to be true. False and false is going to be false. And false and true is going to be false. So notice now that both the negation of P implies Q and P and not Q, they have the same truth values, so they're logically equivalent. Similarly, we can prove logical equivalence without using the truth tables. And we can just do that by checking the equivalent form. So we're going to prove this without using truth tables. Then we need to write the equivalent versions of this implication. So if I have P implies Q and P implies R, remember that P implies Q is equivalent to not P or Q. So I can write this. The first one is equivalent to not P or Q. And so, of course, the second one is going to be equivalent to not P or R. So now, if I use distribution properties, this is equivalent to not P or, and then I'm going to have Q and R. And then by the same equivalence, this is equivalence to P implies Q and R. So recall that this is using this equivalent form. This is equivalent to this. We saw this before. And so that's what we're using to get the property and be able to prove this. Now, we can also prove with a truth table that P equivalents to Q means that P implies Q and Q implies P. So we have P true, true, false, false, Q true, false, true, false. P implies Q means true, false, true, true. And then Q implies P, as we saw before. It was true, true, false, and true. So now if I'm going to do P implies Q and Q implies P, which is one of the ones that I need, I'm going to do the end for this, which is true, false, false, true. And now I'm missing P equivalent to Q. P equivalent to Q is, if they're the same, then it's true, otherwise it's false. So because false is equivalent to false, this is true. And because these are different, then it's false. Now notice that, once again, these columns have the same truth values. True, false, 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 true. And so this means that these two are logically equivalent statements. All right, let's move on to question 18. So we want to do true or false here statements. Says a conditional statement and his contrapositive are always logically equivalent. And this is true. This is something that we mentioned before, which is P implies Q is logically equivalent to negation of Q implies negation of P, which is the contrapositive. A conditional statement, P implies Q, and its converse are logically equivalent. And so this here is going to be false. Okay. The converse, remember, the converse Q implies P, and they're not necessarily equivalents. The converse might be equivalent to the inverse. If a conditional statement is true, then its inverse must be also true. So P implies Q is the original statement, and now the inverse is negation of P implies negation of Q. And so, of course, if this is going to be false, right? You can give some values. Let's say if P is false and Q is true, then P implies Q is going to be false implies true is going to be true, right? But if we have the opposite, which is negation of P implies negation of Q, notice that this will be a true implies false, and this is false. So this is not correct. Now D, the statement P implies Q, is false when P is true and Q is false. This is true. This is the one condition that we have for the implication to be false. Now, question 19, consider the statement, if a number is divisible by 4, then is divisible by 2. Is this a statement true? And the answer is yes. Notice that if something is divisible by 2, so if 4 is divisible by n, it means that n is a multiple of 4. So n is equals 4k for some k that belongs to the integers. But this means that you can see it as twice 2k. So this means that it's a multiple of 2. And hence, 2 divide that number n as well. So now write a converse. Is the converse true? Well, the converse is going to be if it's divisible if by 4. If 2 divides n, then 4 divides n. And this is not necessarily true, or actually this is going to be false. And the example here is 2 divided 6, or 6 is divisible by 2, but not by 4. But 4 does not divide 6. Once again, 6 is 2 by 3, 2 times 3. So that's why you have this. But there's no number such that you can express 6 as 4 times some k, with k in the integers. So this is the notion of divisibility. Now, let's write the contrapositive of this statement. So we have if n is not divisible by 2. So if 2 doesn't, n is not divisible by 2, then it's not divisible by 4. Okay? And this is actually true, since it's equivalent to the original statement, which is true. Right? Now the inverse. The inverse is, once again, if this is P and this is Q, then we have negation of P implies negation of Q. So we're saying if 4 does not divide n, then 2 does not divide n. And this is false. And we can use pretty much the same example that we use for the converse. Okay? Well, actually, the converse and the inverse are equivalent, so it makes sense that we can use the same example. Okay? All right, this is the end of the 2.2 examples.